Okay, so we previously talked about a resting membrane potential that a neuron has. And in lecture 24, we'll talk about how that resting membrane potential is disturbed at the synapse by an impulse. And that disturbance is going to result in a graded potential, which we'll be talking about for this video. So when we're talking about these changes in electric potential, we want to know how to read one of these graphs right over here, right? We're going to see that, there's a resting membrane potential at minus 70. That's all of a sudden disturbed, right? And it's going to, as a function of time, we're going to follow that change in membrane potential. We're going to see that it rises up towards zero, and then it drops back down again, right? As a function of time. So we're going to see a lot of these graphs. So you make sure you understand like what we're talking about when we're looking at a graph like this. So here's I think maybe it makes more sense to people because it's on a different time scale, right? This is a graph in months from April 20. This is about changes up to about now right here. This is actually the daily deaths per 100,000 in the United States, attributed to the coronavirus, right? And if you looked around April, over here, or a little before April, right, 0, 0, 0. And all of a sudden, right around April, right here, we saw the death rates rising and rising and rising until around May or so. And then they started dropping over here, right? So they're recording at any one given time point the number of people who died due to coronavirus at this place. So this chart is following through time, right? The rate basically per 100,000, what happens, right? It started going up and then it dropped down again. Sometime in the summer, we saw it rise again, and then it started dropping back down. And then came fall, the winter season, we saw this big rise, and then now it's dropping way back down, right? Starting around February, March, started dropping way back down until it's predicted to be very low, right? That kind of makes sense about what we're looking at here, right? They could kind of count the number of people at any one point and then graph it like this. You're doing the same thing. You're just monitoring it in a matter of milliseconds, 1/1000th of a second, as your resting membrane potential goes from its resting state at minus 70. And then all of a sudden, there's a disturbance such that this rises up and then falls back down here, right? So that's what you're looking at. Just make sure you understand that. So again, here's the detail part of it, of this depolarizing graded potential. We're looking at the cell membrane. We're recording it at any given point. We got this resting recording microelectrode that's going to tell you the difference between here and here, which again is minus 70 at some point. You have a stimulus of some point, which is going to cause a depolarization event, as we'll see. That is a flood of sodium ions in the area. And with that stimuli here, you're going to see a rise, right? As sodium ions, right, flood this area right here. In this area, which was minus 70, right? They're all going to rush in. And that's going to make it go from minus 70. In this example, right, you're going to record it at 0 milliseconds. And then over here, you'd see it rising. Over here, you'd see it rising. Over here, you start to see it dropping, right? So they're recording it every little second, and they make a graph like this based on time, based on this stimulus right here. Right? So this graded potential, a small deviation from the resting membrane potential, then it's going to occur when some kind of stimuli is causing gated channels, right? Sodium, potassium, calcium, to open or close in an excitable membranes plasma. Right? And for the most part today, we're going to be talking about this depolarization, right? The cell is polarized, and depolarization means it's going towards zero, and then it wouldn't be polarized anymore because there would be no difference between the outside and the inside. So you see over here, it goes at 60, 60, 60. There's something going on. Over here, we're depolarized. All of a sudden starts raising up toward there, doesn't reach it, but it's called depolarization. And then goes back down again. So when the response makes it less polarized, that is towards zero, less negative than minus 60, right? Minus 60, minus 50, minus 30, minus 40, minus 20, minus 10, 0, right? Then it's a depolarizing one. Some stimuli, as we'll see on the next lecture when we talk about synapses, could do the opposite. Instead of saying letting sodium flood in the channel, you might let chloride flow in the channel, right? Chloride ions flow in the channel, and that would make the cell more negative. Or you'd let potassium ions flow out. That would make it more negative. Right? So that's called a hyperpolarization. We only talk about this a little bit when we get to action potentials and the whole phases of action potentials. But we'll talk more about that in terms of graded potentials next time we'll talk about different types of synapses. So mostly we'll be talking about this depolarized, right? For these graded signals, and again, we'll just kind of think about depolarizing ones, right? They're going to vary in the amplitude. You have a small stimulus, right? A little bit of channels open, you get a little small bump like this. Bigger one, bigger bump, bigger one, bigger bump, right? And so they vary in the amplitude of how big they are. This could be, you can get this all over the cell, right? Amplitude is going to depend on how many ligand gated or mechanically gated channels have opened or closed and how long they remain open. Remember, we talked about the acetylcholine. It was spilling out there. And if for some reason you did not remove those acetylcholine, right, the channels kept open and you get a larger depolarization event. So the amplitude of this is going to depend on how many channels are open, basically how much neurotransmitter is still there, and how long they stay open, right? So what happens when there is this stimuli to any one region over here, right? This is, say, a stimuli here. They're artificially doing it. They have a little stimulating thing that's causing all this positive signal to flow inward. So there's a big splash, right? Remember the pond right over here. What happens as, this decays, right? But it's basically going to get smaller and smaller and smaller as it moves away from that initial splash point. Right, so it's going to die out as it moves away. It's going to spread to adjacent regions within the cytoplasm, right? You can have these electric currents moving within here that are going to die out as we go over time because leak channels, sodium, potassium pumps are going to restore that back to resting membrane potential as you move away. Just like in the case of that broken window, right? The guy was sitting inside in his cool house, the window opens, hot air comes in. If he's standing right by the window, you're going to feel this blast of hot air. If you're standing in the other room, you may only feel a little bit, right? And eventually that'll kind of spread out and your air conditioner will kick back in and restore your nice, cool place, right? So again, for these graded potentials, right, you're going to have this stimulation event around the dendrites or wherever there's synapses right here by these ligand-gated channels. That's going to cause a depolarization event. What's going to happen is that's going to cause an influx of sodium ions around here. And because that's going to be local, right in this spot right here. But these positive charge are going to be attracted to the negative charge that's over here. So they're going to start moving over here and over here. Right? They're going to kind of spread out toward the more negative charge. They're going to equilibrate in a way, right? Just like the hot air wouldn't just remain confined to the window. It's going to spread out. But along the way, right, you're going to have these leak channels, which are going to include the potassium ones, which are going to kind of restore that balance over here in some way. And that's going to happen all over the cell, these graded potentials. And then as far as those ion channels go, we'll start to see those voltage gated ones down when you get to the axon hillock and down the axon over here. Right? So what'll happen? Once again, you have a depolarizing event, a stimuli comes in, opens up channels in a given region, a small area of the cell. And these are very small areas, right? Neurons are huge. It's going to be little, very local stuff. When there's positive areas, the ions flow in. You got all these positive charges over here. But what they're looking at are these negative charges right around here, right? So they're going to start moving out. Right? So it's going to spread a little bit. But what also happens is that because all the sodium ions flew in here, you get a negative charge on the outside here. So positive charges start flowing this way as well. Right? So all this is going to create this little wave of electricity spread, both inside the cell and a little bit outside the cell as it moves along there. Right? The current flow is just the sodium ions or calcium, whatever it is, moving around toward their down their electrochemical gradient once they've moved inside the cell right here. All right, so the opening or closing of these ligand-gated channels, in this case, the sodium channel, is going to alter the flow of specific ions, right? Because you had a lot of sodium ions out here. They're all, as soon as they're given a chance, they're going to flood the cell in that localized area. And by localized, it means it's going to be in that area. This closes, right? But the sodium ions are still here. It's going to spread, being attracted to the rest of the negative charge, usually around the cell membrane. Because in reality, it's a little bit localized to the cell membrane. And they're going to go everywhere, like in a circle. Again, the pond, the ripple of a pebble being thrown in a pond right here. And they're going to die out as they move along right there, right? So here's the original point, big depolarization, roughly, I mean, relatively speaking. And as you move away from that stimulus point in either direction, that's going to decrease, right, until you get down to nothing. And so this is a generation of the graded potential right here. Starts off at this, spreads out, weakens as it goes outwards. Right? So if you recorded this with these voltmeters, right, you have the stimulus, local depolarization, a lot of positive charge inside this negative thing, right? And that's causing this to kind of raise up to a certain level over here. And as we move along here, now you record it at some distance away, you'd see it wasn't a -40, but it would be recording -50, right? Because these would kind of peter out a little bit relative to this. And then if you recorded it down over here, close to the axon, you'd see it was even less, right? So it's going to decrease with this time as it moves away from the source. And it hasn't reached this area yet, right? No action potential, which we'll see what I'm talking about there in a minute. All right, that's this graded potential. So sometimes you just get a sub-threshold, right? And for threshold, what we're talking about is, can you make this trigger zone go? At this point down here on the trigger zone, we're going to have a lot of voltage gated channels over here, which are going to react to a certain stimuli by passing on a action potential. And if it's a sub-threshold one, there's a stimuli, which was maybe threshold up here, but by the time it reaches this area, it isn't enough to open up those voltage gated channels. If you have a strong stimuli, that is going to be a couple different ways you can get stronger stimuli. That is enough, right? It's a very strong one, goes way -40. And even though it's dying out a little bit, it's still enough to trigger the so-called action potential. All right, so this is sub-threshold, not enough to go to the trigger zone here, because we're going to get to this next phase here. And the supra-threshold one, which is more than enough over here, and it also will reach it. As it reaches the trigger zone, it's enough to cause this so-called action potential. All right, so that all depends, right, on this whole initial -70, right? You're all starting at -70, and it's easy enough. It's got to kind of break that -70 and get to a certain, say, -55 or something to activate this. If you were already starting at a lower position, then you might find it easier to stimulate the cell. Or if it was at a less than -70, like -90, it would be harder to stimulate the cell. So I just want to mention that in terms of this clinical note. Kalemia, right, means the level of potassium in your blood. This is just a clinical note. Remember, if you have something in your blood right there, a certain potassium level in your blood, it's going to be in the interstitial fluid surrounding the cell. So when you have a normal range, this is keeping your nerve cells at a -70. And you get that normal stimulus, it's going to be acting normally. If you have hyperkalemia, if you have increased blood potassium concentration, that's going to cause your cells to be a little bit more sensitive to stimuli because they're going to be not -70, but they're going to be sitting at -60. Then it'll take a smaller impulse, right? That normally wouldn't trigger something is going to trigger it, right? So you get an action potential off that. That would be too much blood potassium. The opposite way was when you have too little blood hypokalemia, it's going to hyperpolarize and it's going to make it harder for that neuron to fire. Right? So basically what I'm saying is these conditions here, which are caused by various things right here, are going to cause your nerve cells to act really funny, right? They'll either be overactive or underactive, which especially in your heart is going to cause all sorts of problems. Okay, so this is just kind of a clinical note about that and the relationship to potassium and your resting membrane potential, how important that is to keep your interstitial fluid and your ions in homeostatic balance. All right. So here we are back at our depolarized region, right? We stimulated it, we brought a lot of positive ions in, and they're going to flow toward the surrounding areas, causing this kind of wave of positive charge around here that's going to die out on the inside. And then the positive charge over here is going to flow toward the newly created negative charge on the outside. So there's going to be this kind of current flow, and that's going to happen for our graded potential on our dendrites and our cell body, right? The spread of that signal. And we said that if it was a supra threshold or threshold signal that reaches this area, this is when we're going to start to get our action potential going down, right? And this is where we're going to move from a graded to an action potential at this point. And so we'll contrast that with our graded potential, which decays from the point of stimulus and can vary in amplitude, to this action potential, where it's going to be the exact same rise and fall, and it's going to be just as strong as when it started as when it finished. All right, we'll see you next time.